Let's go over how to determine molecular geometries. This is kind of a tricky thing to do, and a lot of students get confused, but let's systematically go through them. And we'll start with the easiest ones. The first thing that you need to do is determine the molecular geometry and the electron pair geometry is to do the Lewis dot structure of the molecule. So for beryllium hydride, okay, I have 2 electrons that come from the hydrogens because I have 2 hydrogens, and then I have 1 beryllium which brings in 2 electrons as well because it's group 2. Okay, so if I were to draw this molecule, beryllium is the one I have the least, so it's going to be the central atom, and I also said the hydrogens have to be terminal, they have to bond at the ends. Okay, I have a total of 4 electrons here. I've used 2, 4, and therefore I'm happy. Now, this can be one of those, it is one of those exceptions to the octet rule. Beryllium doesn't need to have more than those electrons. Okay. So the way this works is I look at the groups around the central atom, and that determines the electron geometry. The groups around the central atom are 2, 1, 2, right? This is 1, this is 2. When I have only 2 groups around the central atom, whether they are atoms or whether they are an atom or a lone pair, well, in this case it will just be the atom, then that means that I have a linear molecule. There is no other way around. This shape of this molecule has to be linear because that is how I maximize how far away they are spaced, right? I have 360 degrees around this atom and I divide it by 2. That means each angle has to be 180 degrees. It's a linear molecule. Now I can have several types of linear molecule. Let's look at this one where I have, once again, let's do a tally, 4 from the carbon, 4 electrons, plus 2 times 6 from the hydrogen or the oxygen, and this is 12 plus 4 equals 16 electrons altogether. Okay. Carbon's going to be the central atom, so I have carbon over here and oxygen over here and oxygen over here. However, they're not very happy. My carbon's not happy because it's got only 4 electrons around. So I'd have to double bond here and I'd have to double bond here to satisfy my carbon. It has 2, 4, 6, 8 electrons around, but I have 16, so I have to distribute 8 more. And those will go as lone pairs on the oxygen, just like this. And remember, we said oxygen will have either a double bond and 2 lone pairs or 2 single bonds and 2 lone pairs. Typically is how it likes to be. So now I have used up all of my electrons, 2, 4, 6, 8, 10, 12, 14, 16, and everybody's happy. Now you can see that once again this will be a linear molecule because I have 2 groups around the central atom. And when I have that, I have a linear molecule. Once again, I have 360 degrees around this carbon. If I divide it by the 2 groups, each of them will have so the angles will have to be 180 degrees. So that is how far apart these 2 groups have to be the most spread out. Now you will see the difference between these 2 molecules. This molecule has 2 single bonds around it. It's still linear, but it has single bonds. This one has double bonds, but it's still linear because it has just 2 groups around that central atom. Let's look at the third example. Once again, let's do a tally. I have 1 electron from the hydrogen, I have 4 electrons from the carbon, and then I have 5 electrons from the nitrogen, giving me a total of 10 electrons. Now, the hydrogen has to be a terminal, so I have to have it at the end somewhere, and then my carbon can be in the middle and the nitrogen on the other side. Well, now this hydrogen is happy, but my carbon isn't because it's got only 4 electrons. So if I double bond it here, I can't do it here because then the hydrogen is not going to be happy. So it's got 2, 4, 6 electrons. It needs 2 more. I need to triple bond it. This is 1, 2, 3, triple bond. Now the carbon's happy, 2, 4, 6, 8. However, I have 10 electrons and my nitrogen only has 2, 4, 6 around it. So the extra 2 electrons will go as a lone pair on this nitrogen. They're on the nitrogen but not on the carbon. So if you take a look at this one, you still have 2 groups around the central atom. And these are lone pairs on the nitrogen, not the central atom. When we talk about geometry, we're talking about the geometry around the central atom. Since I still have 2 groups around the central atom, this is still considered a linear molecule. And this is my third example, to where here I had all 3 of these are linear, but this has 2 single bonds around it. This has 2 double bonds around it, and this has a single bond and a triple bond around it. But they're all linear because they have 2 groups around the central atom. I'm going to erase this, and then we're going to look at the geometry, both electron pair geometry and molecular geometry, when we have 3 groups around the central atom.